type in the chat how comfortable you're feeling in this class on a scale of 1 to 10. 10, it's the easiest class ever. It's so great. 1, you are struggling immensely, right? And then all the numbers in between, you know, somewhere in there. Logan says 7.7. Aiden also says 7, 8. Okay, good. Most people feeling at least over the halfway mark in terms of comfortableness, right? Honestly, looking at people's grades today, you guys are doing pretty well in the class. Keep in mind, progress reports are coming out on Monday, I believe, is when grades are due for teachers. So I just put zeros in for everything up to today for your grades. So go check your grades, right? Keep in mind that you can turn things in until Friday to have them count for your progress report. So try to get a few more things in if you're looking at your grade and you're not quite happy with it. Really, the goal is to pass for the progress report, right? Then you'll have another 6 weeks to raise your grade even further if you'd like. Now, I have built in some extra time towards the end of this class. So the last 2 weeks in January, there will be just a few assignments. There will be the final exam and a reflection assignment. So you'll actually have a lot of time to catch up. So if you're feeling behind or overwhelmed, the last module is actually the hardest one, right? The math comes back and all of the stuff that we've talked about so far comes back. So it can be a little overwhelming, right? So try to get it caught up now so that you can use that extra time for the last module. That would be my advice to you. So we're going to do a little intro to reactions lab today with the most basic of basic reactions. We're going to be looking at the reaction between vinegar and baking soda, right? Household items that you probably have in your house or could easily obtain in your house. You do not have to do this experiment, right? I'm going to do it here live, but you're welcome to do it if you'd like. So we are going to study the effect of temperature on reaction rate. And then we're going to look at and understand how reactions happen. Because as you start going through this next module, you will find out that there are a bunch of different kinds of reactions, right? And they're all labeled and they all have patterns. So being able to look at something and recognize the pattern is going to help you in reactions. So we'll go over a lot of the reactions in more detail. This is just kind of an intro idea. So our hypothesis. Usually, right, in science classes, you're asked, what do you think is going to happen? What's going to happen? Blah, blah, blah. No. In this case, we're going to do a real science hypothesis, which is actually called a null hypothesis. This is where we assume that there will be no change. So we're going to assume that the boiling hot vinegar, the room temperature vinegar, and the freezing vinegar will all have the same length of reaction times. That will maybe be true, maybe not be true. I'm not going to give it away. In order to do this, we have baking soda, we have vinegar at 3 temperatures. And basically all I did for the hot vinegar was I just microwaved it for about 1.5 minutes. It is about 75 milliliters of vinegar in here. So it was boiling. Vinegar boils at a pretty low temperature though, so that doesn't really mean much, but I got it pretty hot. The other one was in the fridge, so it's around 40 degrees, and then our room temperature is about 70-ish degrees. So not a huge difference in temperatures here, but a big enough difference that hopefully we'll see a change. So there are many ways that we could record this, right? We could look at intensity of the reaction, height of the bubbles produced. What we're gonna look at is length of the reaction time. So I'm actually gonna need some volunteers. 3 volunteers, if possible, who can just have a stopwatch going on their phone or on their computer and be in charge of monitoring when one of the reactions stops. Would someone like to volunteer for that? By someone, I mean 3 people like to volunteer for that. All you get to do is record a time. It's pretty easy. Okay, so Oliver, you're gonna be in charge of cold. Your reaction's gonna start in a moment. I'm actually gonna push the camera on them so that you guys can see. But basically, actually, I'm a little worried that I might have done enough vinegar that this is gonna explode out of the Erlenmeyer flask. So I'm gonna go by the sink just in case. Worst case scenario, I I spill vinegar all over myself. Okay, so this might not really be that big of a deal, but this is the cold vinegar. As soon as the vinegar hits the baking soda, Oliver, I want you to push start on your stopwatch. Oh yeah. Okay, and again, it is exploding out, right, which does happen with baking soda and vinegar, right, which is why this is the reaction that people use to make those fake volcanoes. So once the initial explosion has happened, we're gonna be basically looking at this until there are no more bubbles, right? Now, for it to completely end to the point where there are literally 0 bubbles, it might actually go beyond the length of this course, virtual session, I should say, not course. But regardless, yours is still bubbling there, Oliver. We're gonna get the other 2 started. Who would like to stopwatch for the room temperature vinegar? Any volunteers? It's pretty easy to do. Okay, I can do 1, but I need at least 1 other person to record a time here. So I guess I'll start room temperature with my own stopwatch while someone else decides that they want to help here. Okay, so room temperature vinegar, we're gonna say it is starting in just a second here. It's gonna be pretty much the same exact reaction, right? Bubbles exploding out the top. Still pretty vigorous. Honestly, didn't seem as vigorous as the cold. Okay, we'll leave that there. And then, do we have another volunteer? Could Catherine or Logan or Aiden volunteer to do the stopwatch for our hot vinegar? Okay. So, that's fine. I will have to keep track of this time as well. Although I'm a little disturbed. You can. Thank you, Catherine. It's easy. You're just going to push start. And I'm going to let you know when your bubbles have stopped. Ooh. Okay. We're getting close on the cold one, Oliver. Okay, hot vinegar. Oh my goodness. Literally exploding out of the top of this thing. Pretty crazy. Okay, so this is where it's going to be hard. I'm going to be monitoring the vinegars for a second here and also talking to you. Okay, we're going to go ahead and call, we're going to say that room temperature and cold are both done. So go ahead and stop your stopwatch, Oliver. For room temperature, which is the one that I was monitoring, the reaction lasted for about 1 minute and 40 seconds. What was the time on yours, Oliver? 3 minutes, 2 seconds for the cold. And hot is almost done. You will notice, actually, look at the hot one. It turned a different color, right? The regular vinegar color, it's apple cider vinegar, so it's already brownish, but this one's a much darker color from the hot, which is something interesting to observe here, that perhaps the heat actually did something else here than the other 2. Let's see, hot's still going just a little bit, but it's nearing completion here. I'm seeing just a tiny bit of bubbling, so we'll check back in on that one in just a few seconds here. So what you're gonna do on your own is you're gonna create your own line graph here. I recommend that you convert that time into seconds so that it's easier to graph. You could leave it in minutes if you want, but you're gonna be using that graph to predict. So make it as accurate as you possibly can. Okay, sorry, I'm just staring at the vinegar. Okay, we're gonna call the hot one done right now. How long was that, Catherine? Uh-oh. Are you there, Catherine? Okay. How long did it? Okay, there we go. 1 and 20. Perfect. 1 minute. Oops. 20 seconds. Okay, so it does seem like there could potentially be an effect, right? It might actually not have been the effect that you thought was going to happen, right? If you thought something was going to happen, but it does seem that heat potentially maybe increased the time the reaction happened. Maybe, right? Hard to tell, especially since we would need to do probably like, I don't know, 4,000 trials of this to determine that that was true. Bella, welcome. Okay, so we have our times there. And really the point of this experiment is 2 things, right? We're testing a simple variable here, heat, and how it affects reaction rates, but now we're gonna actually break down the chemistry of this reaction because this is actually a pretty complicated reaction, even though it seems simple, right? It's just 2 household ingredients. So here are the formulas for these 2 compounds. Baking soda is, it's called sodium bicarbonate, right, as its official definition, because we have a sodium, we have a carbon 8 polyatomic ion, and we have a hydrogen, right, which makes it the bi. So sodium bicarbonate is baking soda, and then vinegar is also known as acetic acid, right? It is an acid. It's a very unique acid in the sense that it doesn't quite break apart like some strong acids do. But regardless, it's an acid. So this essentially is a base and an acid reacting. Oh yes, I'm sorry. No one even asked for the worksheet other than Bella here. So I did post this in Canvas, but you will be filling out your own version of this, right? So excellent question to ask me for it. Completely slipped my mind. So if you didn't already access it from Canvas, go ahead and click on that link there. Make your own copy, right? I already filled the data in from our trials, so you could just make a copy keeping that data. But that's a good point, Bella, because now you are going to want to actually start interacting on your own worksheet here. Again, you didn't have to write a hypothesis, right? Our hypothesis was that changing the temperature doesn't have an effect. And we have our times there, so that's all we really need from that part. So baking soda, vinegar. Okay, it's a complex reaction that actually occurs in 2 steps. So this is a 2-step reaction, which is pretty, not rare, but most of the reactions we'll look at after this are simpler, if that makes sense. This happens because baking soda is a base and vinegar is an acid. Now, usually when we have an acid-base reaction, you might even want to write this down because it will become helpful for you later. Usually when we have an acid plus a base, we end up getting a salt plus water. That's the basic formula for that. Because what ends up happening is an acid and a base will neutralize each other, right? And at the same time, a salt will produce and it will be dissolved in water, right? So you'll get like a saltwater solution as a result. Chemists use this logic all the time for many reasons, right? But one reason is if you spill an acid, you can pour a base on it and then you'll have water, right? And it's totally easy and safe to clean up. Now, it's not that simple because you have to do it in the right amounts and all that other kinds of stuff, right? But that is the logic behind it. So this is usually what we see when we have an acid and a base reacting is we end up getting a salt and a water. We don't really see that here necessarily, right? So this is kind of what we end up seeing happening. We have our sodium bicarbonate or our baking soda plus our vinegar, right? Notice the subscripts here. Or not subscripts, but the parentheses here, which usually are subscripts a lot of times, they actually tell us the state of matter of our substance. And this is going to become important in reactions because we end up getting this new thing called aqueous. What do you think that could mean? You could Google it if you want, but what does that mean? It's a solution. Yeah, exactly, right? It means dissolved in water. So when things dissolve in water, they behave differently sometimes, right? Specifically ions. There's a difference between having salt and having salt in water. So the way that we differentiate that is by writing this AQ as a state of matter, essentially, which would tell us here actually that this sodium ion is dissolved in water. Now, if we have something that's aqueous, we have to have water, right? Or a liquid. Sometimes things can dissolve in alcohol, but we're not really going to see that in this class. So in this case, the first part of our reaction, we actually end up having, I'm going to move this thing out of the way. We end up having our sodium and our vinegar, our baking soda and our vinegar mixing together, right? They're producing a carbon dioxide gas, which we saw as the bubbles that erupted out, right? They're producing water, which would be expected from an acid-base reaction. However, the ions they produce are a sodium ion and I don't even know what kind of ion that is. That is some kind of polyatomic ion that I don't know what it's called. So it produces these two ions, which usually 99% of the time would form together and make a solid salt. So for example, usually we would see something like this. HCl, hydrochloric acid, plus NaOH, sodium hydroxide, would yield H2O, water, plus sodium chloride, also known as table salt. Right? This is usually what would happen. Now, would these two be dissolved in the water? Yes, right? Most of the time. That's usually where the reaction stops. However, in this case, this reaction is extra special because it continues, right? So there's a double displacement reaction, which we'll talk about in a second, where the vinegar reacts with the sodium bicarbonate to form acetate and carbonic acid. Then they go through a second component. Okay, why am I not able to scroll? Sorry, I'm getting distracted, guys. Haven't done a virtual session in a while, so my brain's like going a million miles an hour. Okay, so the first step of the reaction is what we see right here. We see sodium bicarbonate plus acetic acid is yielding these two things. Right now, as I said, usually we get acid plus base equals salt plus water. We see that in our overall equation, right? But the first step doesn't do that initially. What do you guys notice is happening here that you think might mean double displacement? What does that mean if something is being doubly displaced? What does it mean if something is displacing something else? Don't be afraid to Google, by the way, or take a random guess. You can even just look at what's happening in the reaction and go, oh, I see something that I think it might mean. It's replacing. Exactly. So a lot of these reaction names literally mean what they say. We have a single displacement, which would be one thing replaces another. And then in this case, we have a double displacement where two things are replacing. We also have reactions called things like synthesis, which guess what that means? Putting things together. Decomposition, guess what that means? Breaking things apart, right? So a lot of these reaction names are common sense. They actually do mean what the word is, right? The problem then is applying it to the chemical formula. So in this case, we're going to trace sodium to start. So I'm going to highlight, and you're supposed to also be doing this on your sheet. So you can either watch me do this and do it later, or you can follow along and do it at the same time as me. But let's highlight our sodium element first here. We see sodium there. Why didn't it highlight? Okay. There we go. And we see sodium here. Okay. So what was displaced or changed from our sodium bicarbonate to the products part of our reaction? What switched places or changed? It's kind of hard to see, but I see this C2H3O2, I see that here, right? So that actually came off of the acetic acid and replaced the bicarbonate part of the sodium. Yeah, so Bella's making a great observation. The sodium didn't really change, right? It's true. It might have moved, but it doesn't matter. Really, what you should see is that this second part of our acid here, let's see, we'll highlight in orange, started off being attached to a hydrogen. Now it's attached to a sodium. Okay, that was one of the displacements. We also then see this hydrogen combined with this other hydrogen and the carbonate, so that now we actually have H2CO3. And you are right, Bella, it does make a completely different compound, right? So this HCO3 and this hydrogen combined to make a new thing, right? And what did we make specifically? Well, we made acetate and carbonic acid. So this here is carbonic acid, and this here is acetate. Completely different things from where we started. And it's called double displacement because both of the compounds switched essentially the second part of the compound, right? They switched places. Okay. Now, that was the first step. And again, this is happening so quickly. That was like, you can't see this, right? You can't see these two steps. They look as one step. However, we know they're happening as two steps. So carbonic acid is unstable and it won't remain how it is. So it undergoes a decomposition reaction where literally it breaks apart and decomposes. And it produces the bubbles that we see as CO2. So the CO2 is actually coming from this carbonic acid getting broken down into water and CO2. So we do make a salt, right? Acetate is technically a salt. However, we also produce a gas because we also made an acid that decomposes, if that's making sense. Again, a lot of this stuff you might be going, what, right? But I'm kind of talking the talk so that when you go through some of these lessons, you go, oh yeah, I remember double displacement. I remember decomposition, right? And I kind of already told you what it means because I got ahead of myself, right? But basically this carbonic acid will decompose into water and carbon dioxide. And again, all of this happens instantly. The displacement happens and the carbonic acid immediately breaks down. So that we end up getting our final equation, right? Which sort of shows the summary. Most equations show a summary, right? Which is that we started with a base, sodium bicarbonate, and an acid, acetic acid. We ended up getting carbon dioxide, which we saw as the bubbles, water, which is still left over in our beaker, or Erlenmeyer flask technically, sodium as an ion, and whatever that is called as an ion, right? I'm gonna guess that's called, I think it's called acetate actually. That would make sense. Figured it out. An acetate as an ion, right? So those two are ions because they're dissolved in the water. Okay, so that was a lot to digest, right? The main things that I want you to get out of this are that reactions have patterns. As you go through these lessons, write down what the pattern is, right? We'll do a little bit of work with that together. But for example, in an acid-base reaction, I would write something like this. Acid plus base equals salt plus water. I would write an example. Then anytime I see something that I think might be an acid-base reaction, I would follow my pattern. Now here's kind of a hard question. How do I know that something is an acid? Unless someone tells you, and then you know. But how would I know something is an acid just from looking at the formula? So how would I know that something is an acid? Here's a hint. Look at the formulas that we know are acids. Okay, here's one. H2CO3, that's an acid. Okay, here's an acid, HC2H3O2. That's an acid. Here's one, HCl. Contains H, not just contains H, although that is definitely true. Usually, the H's are written in front of an acid. Not only does it contain hydrogen, but it actually means they're hydrogens that can be released into solution, right? That's how something is acidic, is that it releases hydrogens and they're floating around in the solution, and that makes something acidic. Right now, there are different types of acids. There are strong acids, they release all of their hydrogens. And then there's weak acids where they release some. So usually these type of acids where you have more than one hydrogen, for example, are usually weak. Not always, but usually. So if you see something with an H in front of it, that should be a huge signal to your brain to think acid. So acids have hydrogens in front. What about a base? How would we know something is a base? Just from looking at it. That's a good guess, because we have NaOH here. We conveniently have the same compound, sodium, involved. So that's a good guess from Logan. Actually, the OH. So OH is what tells us that something is a base. Bases have hydroxide polyatomic ions. Oops. So base equals OH somewhere, right? Usually it will be at the end of a compound. Now, is that always true? No, because here we have sodium bicarbonate, which is a base, and I don't see an OH here, right? So that's not always true. Same with the acid thing. There will be acids that don't have hydrogens in front, unfortunately, right? Chemistry is all about breaking the rules, but these are good guidelines to start thinking about it. So the other thing is, if you can't figure out what kind of reaction it is, you've looked at it and you've went through all your options and you're not sure, it's probably acid-base. Sometimes it's hard to tell that that's what it's going to be, but if you've exhausted all of your options, then you should try acid-base and see if it works. Basically, you should ask yourself, can I make water out of this? It's easy in this sodium hydroxide and hydrochloric acid situation, right? Because you can literally see water. You can see it. You can see the hydrogen here, and you can see the OH here, right? And those things become water when you combine them together. And then the Cl and the sodium are left. In other situations, like here with our baking soda vinegar, not quite as easy to see, right? I see an H here, but I'm not 100% sure where my OH is. Maybe it's here, right? So it gets a little confusing sometimes, but it's a good way to figure out if it's an acid base. Look for the H, look for the OH. Oops, I didn't mean to erase that. And then see if you can make water. Okay, so to summarize very quickly before you guys go off on your own, you're going to be answering these conclusion questions at the bottom of the lab on your own. You're also going to be constructing a line graph, right? So those are the two things you're going to do independently after this. Graph based on the reaction time that we had. Again, my recommendation is convert to seconds. Then answer these three conclusion questions. Before I let you go, though, I'm going to summarize, and we're going to talk about what this means to accept or reject a null hypothesis, which some of you might already know if you took bio last year. But to summarize, what kind of reaction did we see in this lab? And that's a pretty hard question to answer because there's more than one answer. Maybe I'll rephrase it to which kinds, with an S, of reactions did we see in this lab? quick and slow. Okay, that is technically a correct answer. What I'm looking for is things like the word decomposition, right? We saw a decomposition reaction right here. We saw an acid break down into water and a gas. We also saw a double displacement reaction, right? Where we saw two things switching places in the first step of this. Did you see apple cider being made? No. No one, apple cider vinegar, but we didn't make anything out of it. You just mixed it with that, yeah. Oh, well, sure. I joked about it, but it does look like apple cider, right? Although I guarantee if you took a drink of it, it does not taste like apple cider. Yeah, so we saw two types here, decomposition and double replacement, right? The other overall reaction that I talked about, because it is technically an example of this, is an acid plus base reaction, right? Where acids plus bases make a water and a salt. Now, the reason I picked this reaction, right, is because this is something that a lot of people have done before and are super familiar with, right? Oh yeah, baking soda vinegar, da 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 da. Well, it's actually a pretty complicated reaction. So it kind of gives you some insight into that even something that looks simple may not actually be simple chemically. Imagine the person that figured out that this happened in 2 steps, right? That was definitely not always thought. Okay, so we're going to talk about the first question on the conclusion together. Do we accept or reject our null hypothesis? Well, what was our null hypothesis? It was, we will assume that changing the temperature of vinegar will do nothing for the length of the reaction time. In other words, there's going to be no effect. Hot's going to be the same as cold, it's going to be the same as room temperature. That's our null hypothesis. We assume there's nothing happening. We would accept that if that's true. We will reject that if it's not true. So what do you guys think based on the data that we collected here? Are you going to accept or reject that concept? Reject. Right now, you could argue that you accept, right? Sure, it looks like the time kind of doubled between room temperature and ice cold, but realistically, you could say, I accept my null hypothesis because this is not enough data for me to determine, right? That's an answer that you could say. However, really, you guys are right. Reject is the correct answer here because it looks like there is a change, right? There is something going on here. Ice cold took 3 minutes and hot finished in just over a minute, right? Hot also changed a funky color that did not happen on the other ones. So, you know, that does seem like there was something going on. Again, if this was a real science experiment that we were doing to prove something, right, we would do it probably like 5,000 times before we would say that we reject. But that is a commonly known thing, right? Heat makes reactions go faster. Guess what? We just showed that that's true. Okay, so you guys are going to answer these 3 questions. We kind of just answered the first one together, so that's easy. And otherwise, that's pretty much all we're going to be doing this week. Next week, we're going to start talking about the different types of reactions. I also included, for those of you who haven't done your DBA, I know a few people emailed me and said, hey, when can I do my DBA with you? And I said, wait till this virtual session, right? So I did actually include the DBA questions in this virtual session assignment. So if you go all the way to the bottom of modules and you click on virtual session 8, intro to reactions, right, you will see a link to this lab, and then you will see these DBA questions. So if you haven't gotten a chance to do the DBA yet, I know I emailed a few people the questions. You can copy and paste those questions and use those to turn in your DBA. Right, we're gonna do a pretty simple one this time just because a lot of these questions were kind of like, you know, did you understand this or not kind of questions. Not a lot of discussion involved. However, when we do this reaction stuff, there's going to be way more discussion stuff. So keep in mind your DBA questions are linked there if you need them. And otherwise, get as much stuff turned in as you can for progress report grades. Right? I'm gonna be grading like crazy on Friday. So keep turning stuff in. Otherwise, does anyone have any questions related to this assignment, to the DBA, to anything else in the class? Okay, Bella says nope. I assume she speaks for the group. Thank you for those of you who helped with the timing. And I will talk to you guys next week. And we'll keep talking about reactions. Have a great rest of your week.